This quantum paradox revealed a contradiction physics can't explain. There is a moment in the history of science that almost nobody talks about correctly. Not because it was hidden, not because the data was lost, but because what scientists discovered was so disturbing that even today, physics still does not know how to explain what it truly means. For centuries, humanity believed the universe obeyed clear rules. Every planet moved according to predictable laws. Every cause created an effect. Every object existed in one place at one time. Reality felt stable, solid, objective. Then quantum physics arrived and shattered that certainty. Suddenly, particles began behaving like ghosts. Tiny fragments of matter appeared capable of existing in multiple places simultaneously. Some changed behavior the instant they were observed. Others seemed mysteriously connected across impossible distances, as if space itself meant nothing to them. At first, scientists assumed the problem was incomplete information. Maybe the instruments were flawed. Maybe hidden variables existed behind the scenes. Maybe reality still made sense in ways humanity simply had not discovered yet. But the deeper physicists explored the quantum world, the worse the contradiction became. Experiments started producing results that sounded less like science and more like science fiction. Particles communicating instantly across the universe. Effects appearing before causes. Decisions made in the present influencing measurements recorded in the past. And perhaps the most terrifying implication of all, reality itself may not fully exist until it is observed. Think carefully about that. Everything around you feels stable because your brain evolved to survive inside a predictable world. You trust that the moon remains in the sky even when nobody looks at it. You trust that time flows forward. You trust that the universe exists independently of your awareness. Quantum mechanics challenges every one of those assumptions, and hidden inside one particular experiment lies a paradox so unsettling that it divided the greatest physicists in history. Even now, after decades of research and astonishing technological advances, there is still no universal agreement about what the experiment actually revealed. Not because the mathematics failed, the mathematics worked perfectly. That is precisely what terrified them. The equations predicted reality with astonishing accuracy while simultaneously destroying humanity's most fundamental understanding of existence itself. Some scientists concluded that reality splits into multiple universes every second. Others argued that consciousness may play a direct role in shaping physical events. Some believed causality itself might be an illusion created by the limitations of the human mind. And one physicist, perhaps more than any other, refused to accept where these discoveries were leading: Albert Einstein. One of the greatest scientific minds humanity has ever produced looked directly at quantum mechanics and saw something deeply wrong hiding beneath its success. He believed the universe had to remain objective, rational, and independent from observation. But the universe did not cooperate. Because one experiment eventually revealed a contradiction so profound that physics itself still stands divided at the edge of understanding. Tonight, we are going to enter that contradiction, not as students in a classroom, but as witnesses to one of the strangest discoveries in human history, a discovery that may force us to confront an impossible question: what if reality is not what we think it is? The illusion of certainty. Before quantum physics shattered humanity's understanding of reality, the universe felt beautifully predictable. For generations, science appeared to be moving toward absolute certainty. Every discovery strengthened the belief that reality operated like a perfect machine. Planets followed precise orbits. Gravity obeyed elegant mathematical laws. Light traveled through space with measurable consistency. Cause always produced effect. The cosmos seemed ordered, rational, and ultimately understandable. Humanity felt victorious, and in many ways, it was. Through physics, human beings transformed from fragile creatures staring fearfully at the stars into a species capable of calculating eclipses centuries in advance, splitting atoms, walking on the moon, and mapping the birth of galaxies billions of light years away. The universe appeared governed by rules that could be decoded. Isaac Newton helped establish that confidence. His equations described motion so accurately that they became the foundation of modern civilization. The same mathematics predicting the fall of an apple could also predict the movement of worlds. Suddenly, nature no longer looked chaotic. It looked mechanical, reliable, almost clock-like. Then came Albert Einstein. Einstein did not destroy this vision of reality. He perfected it. His theory of relativity transformed space and time into something dynamic and interconnected, yet still deeply logical. Gravity was no longer an invisible force pulling objects together. It became the curvature of space-time itself. Massive stars bent the fabric of reality like enormous weights pressing against a cosmic surface. It was revolutionary. But even inside Einstein's strange new universe, reality still remained objective. Events had causes. Objects possessed properties whether anyone observed them or not. The universe existed independently of the human mind. This idea mattered more than most people realize, because science itself depends on the assumption that reality exists consistently, whether humans observe it or not. A scientist performing an experiment in Tokyo should obtain the same result as another scientist in New York, because the laws of nature are presumed to exist outside personal perception. Reality was not supposed to care about observers. Then physicists began investigating the microscopic world, and everything started breaking apart. Inside atoms, particles refused to behave like ordinary objects. Electrons did not orbit nuclei the way planets orbit stars. Light behaved both as a wave and as a particle. Matter seemed to flicker between possibilities instead of existing in fixed states. The deeper scientists looked, the stranger reality became. Imagine shrinking yourself smaller and smaller until entire galaxies tower above you like distant clouds, smaller than cells, smaller than molecules, smaller than atoms themselves. At that scale, nature stops behaving normally. Particles appear in locations they should not occupy. Some pass through barriers as if solid matter does not exist. Others remain mathematically undefined until measured. It becomes impossible to know both the exact position and momentum of a particle simultaneously, no matter how advanced the technology becomes. This was not a limitation of instruments. It was reality itself behaving differently, and the implications were catastrophic. Because if the universe becomes fundamentally uncertain at its deepest level, then certainty itself may be an illusion constructed by human perception. Physicists struggled desperately to preserve order. They invented probabilities, wave functions, and quantum models capable of predicting outcomes with extraordinary precision. The calculations worked so well that quantum mechanics became the most successful scientific framework ever created. There was only one problem. Nobody understood what the equations were actually describing. Even worse, some interpretations implied that particles did not possess definite properties until observation occurred. Think about how disturbing that idea truly is. Imagine placing an object inside a sealed box. Common sense says the object already possesses definite characteristics, whether you open the box or not. A ball remains red even in darkness. A coin remains heads or tails before you look at it. Quantum mechanics suggested something radically different. At the smallest scales of existence, reality itself might remain undefined until interaction takes place. Not hidden, undefined. As if nature refuses to fully decide what is real until the universe is forced to produce an outcome. This was the fracture line beneath modern physics, and most people never realized how deep it went. Because while the public celebrated scientific progress, many physicists privately confronted a terrifying possibility. The universe might not operate according to objective reality at all. Then came an experiment so bizarre that it pushed this contradiction beyond the limits of logic itself. An experiment where the present appeared capable of influencing the past. An experiment that made some scientists question whether time itself was truly real. The experiment that should have been impossible. In 1978, physicist John Wheeler proposed an experiment so disturbing that even many scientists struggled to accept its implications. Wheeler was not a fringe thinker. He was one of the most respected theoretical physicists of the 20th century, a man who helped shape our understanding of black holes, space-time, and quantum mechanics itself. But the question haunting him was terrifyingly simple. What if reality does not decide what it is until the very moment we observe it? To understand why this question became so dangerous, imagine a single photon traveling through space. A photon is a particle of light. According to classical intuition, it should behave like a tiny object moving along a specific path from one point to another. Simple, direct, predictable. But quantum mechanics had already revealed something deeply unnatural about light. Under certain conditions, a photon behaves not like a particle, but like a wave spreading through multiple possible paths simultaneously. This strange behavior appears most clearly in the famous double-slit experiment. When scientists fire photons toward a barrier containing two openings, something impossible seems to happen. If nobody measures which slit the photon passes through, the photon behaves like a wave and interferes with itself, creating an interference pattern on the screen behind the barrier. But the instant scientists observe which path the photon takes, the interference pattern disappears. The photon suddenly behaves like a normal particle. Observation changes reality. That alone was unsettling enough. But Wheeler wanted to push the paradox further. He proposed a terrifying modification. What would happen if scientists waited until after the photon had already passed through the slits before deciding whether to observe its path? Think carefully about what that means. The photon would already have traveled through the experimental setup. The event should already belong to the past. Classical logic says the photon must have already chosen whether it behaved as a particle or a wave. Yet Wheeler suspected quantum mechanics would produce a different answer. And when versions of the experiment were eventually performed, the results became one of the strangest discoveries in the history of science. The photon behaved as though the later measurement retroactively determined its earlier behavior, as if the particle somehow knew what scientists would decide in the future. If the experiment was configured to reveal path information, the photon behaved like a particle. If the setup prevented path information from being known, the photon behaved like a wave. But the truly disturbing part was this. The choice about how to measure the photon occurred after the photon had already entered the apparatus. From the perspective of ordinary reality, it should have been too late, and yet the equations worked perfectly. The universe behaved exactly as quantum mechanics predicted. Imagine standing at the edge of a road and watching a car pass by. Hours later, you make a decision, and somehow that choice changes the path the car already took earlier that day. That is how absurd Wheeler's experiment appeared. And then things became even worse, because physicists later developed an even more unsettling variation called the delayed choice quantum eraser. This version introduced entangled particles linked together in such a profound way that measuring one instantly affects the other regardless of distance. In the experiment, one photon travels toward a detector, while its entangled partner travels through a separate system capable of either preserving or erasing information about the original photon's path. Here is where reality begins to feel genuinely unstable. When path information remained available, the interference pattern vanished. When path information was erased, the interference pattern returned. But in some versions of the experiment, the decision to erase or preserve the information happened after the first photon had already been detected. The measurement appeared to reach backward through time. Physicists immediately argued over the interpretation. Some insisted no information was literally traveling into the past. Others argued the experiment only revealed limitations in how humans visualize quantum systems. But beneath the technical debates, the deeper horror remained untouched. The universe did not behave like a stable sequence of objective events unfolding independently through time. Instead, reality seems strangely dependent on observation, information, and probability, as if the universe exists in a fog of possibilities until interaction forces one version of reality to emerge. And once scientists realized this contradiction was real, another terrifying question emerged. If observation affects reality at the quantum level, what exactly counts as an observer? Einstein's biggest nightmare. Albert Einstein spent his life searching for order hidden beneath the chaos of the cosmos. To the world, he became the symbol of genius, the man who bent space and time, the physicist who revealed that gravity was not a force, but the geometry of reality itself. His ideas transformed modern science so completely that even today, satellites orbiting Earth must account for relativistic distortions predicted by his equations. Einstein trusted the universe, not emotionally, mathematically. He believed reality possessed an underlying logic independent of human perception. The moon remained in the sky whether anyone looked at it or not. A star exploding in a distant galaxy did not require observation to become real. Nature existed objectively, governed by consistent laws that no observer could alter simply by watching. Then quantum mechanics arrived like a crack spreading through the foundations of existence. At first, Einstein helped create the very theory he would later resist. His work on light quanta became essential to the birth of quantum physics. Ironically, the revolution threatening objective reality began partly through his own discoveries. But as the implications became clearer, Einstein grew increasingly disturbed. The mathematics worked with astonishing accuracy. No scientist could deny that. Quantum mechanics predicted experimental outcomes more successfully than any theory in human history. Yet beneath its predictive power, Einstein sensed something deeply broken. The theory described probabilities instead of certainties. It suggested particles existed in undefined states before measurement. Worst of all, entangled particles appeared capable of influencing one another instantly across enormous distances. This violated one of Einstein's most sacred principles: nothing should travel faster than light. According to relativity, the speed of light was not merely fast, it was a fundamental limit built into the architecture of reality itself. No signal, no force, no information should cross that boundary. But quantum entanglement seemed to ignore the rule completely. Two particles born from the same interaction could become linked in such a profound way that measuring one instantly determined the state of the other, even if they were separated by light years of empty space. Einstein hated this implication. He called it spooky action at a distance. Not because it sounded mysterious, because it sounded impossible. To Einstein, quantum mechanics had to be incomplete. Hidden beneath the probabilities, he believed deeper variables still existed, unseen mechanisms preserving objective reality behind the scenes. The apparent randomness of quantum behavior must simply reflect humanity's ignorance, not the true nature of existence itself. He famously rejected the idea that chance governed the universe. God does not play dice with the universe, but the universe remained silent, and quantum mechanics kept winning. In 1935, Einstein and his colleagues Boris Podolsky and Nathan Rosen published what became known as the EPR paradox, one of the most important thought experiments in scientific history. Their goal was not to destroy quantum mechanics. It was to expose what they believed was its fatal contradiction. They argued that if quantum entanglement were truly real, then either information traveled faster than light or particles lacked definite properties until measurement occurred. Both possibilities seemed absurd. Either relativity broke or objective reality broke. Einstein assumed nature would never allow such madness. For decades, the debate remained unresolved. Many physicists quietly avoided asking what quantum mechanics actually meant. They focused instead on calculations, predictions, and practical applications. Quantum theory worked too well technologically to abandon, even if its implications felt philosophically catastrophic. Then, in 1964, physicist John Bell changed everything. Bell developed a mathematical theorem capable of testing whether hidden variables truly existed beneath quantum mechanics. For the first time, Einstein's objections could move from philosophical debate into experimental science. The results would become devastating. Over the following decades, increasingly sophisticated experiments tested Bell's inequalities with extraordinary precision. Again and again, the universe sided against Einstein. The hidden variable explanation failed. Entangled particles behaved exactly as quantum mechanics predicted. Instant correlations appeared real, not because particles secretly communicated through ordinary space, but because reality itself seemed fundamentally non-local at the quantum level. This word changed everything. Non-local. It means that the universe may not be built from isolated objects interacting only through nearby contact. At the deepest layer of existence, separation itself may be partially illusory. Two particles separated by galaxies could still belong to one indivisible quantum system. Imagine how terrifying this realization truly is. Everything your mind experiences suggests separation. You feel distinct from the stars. Your body feels separate from distant galaxies. Space appears to divide objects into isolated locations. Quantum entanglement whispers something profoundly different. The universe may be far more interconnected than human consciousness can naturally comprehend. And Einstein, perhaps the greatest defender of rational reality in modern history, spent the final years of his life fighting against that possibility. But the experiments never stopped. And with every new confirmation, the contradiction grew deeper. Because physicists now faced a reality even stranger than faster-than-light communication. A universe where the act of observation itself might participate in shaping what becomes real. The contradiction no one can solve. By the late 20th century, physicists found themselves trapped inside a scientific nightmare. Quantum mechanics was undeniably correct. The equations predicted reality with astonishing precision. Every experiment, every technological breakthrough, every microscopic interaction continued confirming the theory again and again. Modern civilization itself quietly depends on quantum physics. Smartphones, lasers, MRI scanners, semiconductors, quantum computing research, all of it emerges from principles scientists can calculate with extraordinary accuracy. And yet, beneath that success, a terrifying question remained unanswered. What is quantum mechanics actually describing? Not how it predicts outcomes. What reality itself truly is. This became the contradiction at the heart of modern physics. Because when physicists attempted to explain what quantum mechanics meant beyond the equations, reality fractured into radically different interpretations, each one stranger than the last, and no experiment could definitively prove which interpretation was correct. Imagine discovering a machine capable of perfectly predicting the future while having absolutely no idea how the machine functions internally. That is the position physics entered. The calculations worked. Reality stopped making sense. One of the oldest interpretations became known as the Copenhagen interpretation, developed largely through the work of Niels Bohr and Werner Heisenberg. According to this view, quantum particles do not possess definite properties before measurement. Instead, they exist as probability waves containing multiple possible outcomes simultaneously. Only when observation occurs does the wave function collapse into a single measurable reality. Think about what this implies. Before observation, an electron may not truly possess a specific location. Reality exists as potential rather than certainty. The universe remains suspended between possibilities until interaction forces a definite outcome to emerge. This interpretation solved the mathematics elegantly, but philosophically it felt devastating, because it implied that objective reality may not exist independently in the way human intuition assumes. Einstein despised this idea. Many scientists still do. So alternative interpretations emerged. Then came one of the most disturbing proposals ever seriously considered by science, the many worlds interpretation. According to this theory, the wave function never collapses at all. Every quantum possibility actually occurs. Every single one. When a quantum event produces multiple outcomes, reality itself splits into parallel branches. In one universe, a particle moves left. In another, it moves right. In one version of existence, a star explodes. In another, it survives slightly longer. Countless invisible universes constantly divide from one another every fraction of a second, not metaphorically, literally. If many worlds is true, then unimaginable versions of reality exist beyond your perception right now. Entire alternate histories branching endlessly through an incomprehensibly vast multiverse. A universe where every possible version of you may exist somewhere across the quantum landscape. Some physicists embrace this interpretation because it preserves mathematical consistency without requiring mysterious wave function collapse. But emotionally, the idea felt almost unbearable, because it transformed reality into something infinitely stranger than humanity had ever imagined. Then another interpretation pushed the contradiction into even darker territory: pilot wave theory. Originally proposed by Louis de Broglie and later expanded by David Bohm, this model suggested particles possess definite positions at all times, guided by an invisible quantum wave operating beneath reality. At first glance, this restored order. Particles remained objectively real, but the price was terrifying. The guiding wave appeared fundamentally non-local, meaning distant events could remain connected instantaneously across space-time itself. In this interpretation, the universe behaves less like isolated objects interacting mechanically and more like a hidden interconnected system unfolding beneath visible reality, as if space-time itself were only the surface of something deeper. Then came perhaps the most controversial possibility of all. What if consciousness plays a role in collapsing quantum probabilities into physical reality? Some interpretations cautiously explored whether observation requires awareness itself, not measurement by machines, not physical interaction alone, conscious experience. The implications became explosive. Could the human mind participate in shaping reality at the quantum level? Most physicists remain deeply skeptical of this idea, and many reject it entirely. Yet the fact that such questions even emerged inside legitimate scientific discussion reveals how profoundly quantum mechanics destabilized humanity's understanding of existence. Because underneath every interpretation lies the same terrifying truth. Nobody knows what reality fundamentally is, not completely, not even now. Modern physics possesses equations of breathtaking power while lacking consensus about what those equations describe beneath the surface. And the deeper scientists look, the the more unstable reality appears to become. Matter dissolves into probabilities, space loses its independence, time behaves strangely, observation affects outcomes. Separation becomes questionable. Causality itself begins to blur. It is as though the universe resists being reduced into a simple human story. And somewhere inside this contradiction, another terrifying possibility slowly began emerging. What if space, time, matter, and reality itself are not fundamental at all? The possibility that reality is not fundamental. For most of human history, reality seemed obvious. Space was the stage where existence unfolded. Time flowed steadily forward. Matter formed the substance of the universe. Galaxies drifted across enormous cosmic distances inside a vast physical arena, extending endlessly through the dark. It felt natural to assume these things were fundamental, permanent, absolute, but quantum physics began eroding that certainty piece by piece. And as physicists pushed deeper into the structure of reality, a deeply unsettling possibility emerged. What if space and time themselves are not the foundation of existence? What if they are only consequences of something deeper? At first, this idea sounded absurd. After all, everything humans experience depends on space and time. Every memory, every movement, every star burning in the night sky. The entire story of civilization unfolds inside their framework. Yet modern physics keeps pointing toward the same disturbing conclusion. The universe may not be built the way it appears. One clue emerged from black holes. Black holes are among the most violent objects in the cosmos, regions where gravity becomes so intense that not even light can escape. According to Einstein's equations, a sufficiently compressed mass curves space-time so severely that reality itself collapses inward. But black holes created a paradox. When physicist Stephen Hawking discovered that black holes slowly emit radiation and eventually evaporate, scientists encountered a terrifying contradiction. If a black hole disappears completely, what happens to the information describing everything that fell inside it? Quantum mechanics says information cannot truly vanish, but relativity seemed to imply that black holes destroy it forever. Both theories could not simultaneously remain correct, and once again, physics entered crisis. The contradiction forced scientists to reconsider something radical. Maybe information, not matter, is the deepest layer of reality. This idea sounds abstract until you realize what it actually implies. Everything you experience, your body, memories, emotions, the stars above Earth, every atom in your brain, may ultimately emerge from informational structures beneath physical existence itself. Some physicists began describing reality less like a machine made of objects, and more like a computational process generated from relationships, probabilities, and encoded information. Then the holographic principle appeared. According to this astonishing idea, the three-dimensional universe may function like a projection emerging from information stored on a lower dimensional boundary. Imagine standing inside a hologram without realizing it. Everything feels real, depth exists, distance exists, objects possess form and structure. Yet the true information defining the system exists elsewhere. Some of the world's most advanced theories in theoretical physics now seriously explore this possibility. And the implications become even stranger. Because if space-time emerges from deeper quantum relationships, then space itself may not be fundamental. Distance may be partially illusory. Separation may not exist in the way human consciousness naturally perceives it. Quantum entanglement suddenly begins looking less like particles communicating across space and more like evidence that space itself emerges from hidden connections beneath reality. The contradiction starts folding inward. Reality no longer resembles isolated objects moving through empty space. Instead, the universe begins looking like an interconnected network of probabilities woven together beneath perception. And then comes the truly terrifying question: where does consciousness fit into all of this? Human awareness remains one of the greatest unsolved mysteries in science. Neuroscience explains patterns of brain activity, but nobody fully understands how physical processes produce subjective experience itself. How does matter become awareness? Why does the universe contain observers capable of experiencing existence from the inside? Some physicists and philosophers cautiously began wondering whether consciousness is not merely a byproduct of reality, but part of its deeper structure. Not magical, not supernatural, something even stranger. What if conscious observation reflects an interaction between mind and the probabilistic fabric underlying physical existence? Most scientists reject strong versions of this claim, and no consensus exists. But the fact that serious discussions emerged at all reveals how unstable the foundations of reality have become. Because once quantum mechanics enters the picture, even the distinction between observer and observed begins to blur. The human mind evolved to survive on the surface of reality, not to comprehend its deepest architecture. Our brains were shaped by forests, predators, weather, and survival across ordinary scales of existence. Nothing in human evolution prepared consciousness to intuitively grasp quantum probability fields, non-locality, emergent space-time, or multidimensional informational structures. And yet, the equations continue pointing there, as though science itself has wandered beyond the limits of ordinary intuition. The deeper humanity searches for the foundation of reality, the more reality dissolves beneath observation. Matter becomes energy, energy becomes probability, probability becomes information. And somewhere beyond that horizon, physics encounters something almost unbearable: the possibility that the universe is not a collection of things, but a process, a vast unfolding field of relationships waiting to become real through interaction itself. And standing at the center of that mystery is humanity, a species of conscious beings staring into the cosmos, while the cosmos stares silently back. The silence at the edge of human knowledge. There is a moment that arrives in every great scientific journey when discovery stops feeling triumphant and begins feeling deeply unsettling. Humanity once believed knowledge would eventually illuminate every corner of existence. Every mystery appeared temporary. Every unknown looked conquerable. Science became a torch carried against the darkness, revealing the hidden machinery of the cosmos piece by piece. But quantum physics led humanity somewhere unexpected, not toward certainty, toward the edge of comprehension itself. Because after more than a century of experiments, equations, and astonishing discoveries, physicists still cannot answer one haunting question. What is reality? Not mathematically, fundamentally. The deeper humanity investigates the universe, the more existence resists ordinary explanation. At the largest scales, galaxies drift through expanding cosmic darkness shaped by invisible forces scientists barely understand. Dark matter surrounds entire galaxies while remaining undetectable directly. Dark energy pushes the universe outward faster and faster, for reasons still unknown. And at the smallest scales, quantum mechanics transforms reality into a storm of probabilities where certainty dissolves before observation. It is as though the universe becomes less intuitive the closer humanity approaches its foundations. Think about how strange this truly is. The human species evolved on a tiny world orbiting an ordinary star at the edge of a single galaxy among trillions. Every instinct inside the human brain was shaped by survival within a narrow range of experience. Our senses perceive only fragments of reality. Our intuition understands only the scales necessary for survival. Yet somehow, against impossible odds, consciousness emerged capable of questioning the cosmos itself. A collection of atoms became aware enough to ask where atoms come from. That alone is extraordinary. But perhaps even more extraordinary is this: the universe may not be obligated to make sense to the human mind. This realization quietly haunts modern physics, because every attempt to fully explain quantum reality eventually collides with concepts that strain the limits of language itself. Scientists use equations because ordinary words begin failing. Mathematics continues deeper into reality than intuition can comfortably follow. And beyond a certain point, the universe stops resembling anything human beings evolved to understand naturally. Particles become waves, time loses clarity, space becomes relational, observation influences outcomes, possibilities coexist before measurement. Reality behaves less like an object and more like an unfolding process. At times, it almost feels as though the universe is warning humanity that existence is far stranger than consciousness was designed to perceive. Even Einstein sensed this tension. Near the end of his life, despite helping revolutionize modern physics, he remained uncomfortable with the probabilistic nature of quantum mechanics. Not because he lacked intelligence, but because the implications wounded something deeper: the belief that reality must ultimately remain rational in ways human minds can fully grasp. Yet experiment after experiment continued revealing a cosmos operating beyond ordinary intuition. And still, humanity keeps searching. That may be the most beautiful part of this entire story. Despite confronting mysteries capable of destabilizing our understanding of existence itself, humanity refuses to stop asking questions. Across observatories, laboratories, particle accelerators, and equations written in silence late at night, the species continues pushing against the unknown. A fragile civilization on a small planet attempting to decode the architecture of reality itself. There is something profoundly moving about that. Because science is not merely the accumulation of knowledge, it is an act of confrontation, a refusal to look away from mystery. Quantum mechanics revealed contradictions physics still cannot fully explain. It shattered certainty. It destabilized reality. It forced humanity to question causality, observation, space, time, and the nature of existence itself. And perhaps that is why this paradox matters so deeply. Not because it gives humanity answers, but because it reveals how much remains hidden beyond the horizon of understanding. Somewhere in the darkness beyond human intuition, reality continues unfolding according to laws stranger than imagination itself. And maybe the greatest discovery waiting ahead is not a final equation or unified theory. Maybe it is the realization that mystery is not a temporary flaw in human knowledge. Maybe mystery is woven into the structure of existence itself. Because the closer humanity approaches the foundations of reality, the more the universe transforms from a machine into something almost dreamlike, a cosmic ocean of possibility, silent, infinite, watching. Final revelation. The universe may not be what we think it is. For centuries, humanity searched for the ultimate truth hidden beneath reality, a final law, a final equation, a perfect explanation capable of revealing why the universe exists and how everything fits together. That search transformed civilization. It carried humanity from caves to telescopes, from myths to mathematics, from staring helplessly at the stars to measuring the age of galaxies billions of light years away. And yet, after all that progress, modern physics arrived at a conclusion more unsettling than ignorance itself. Reality may not behave according to the rules human beings instinctively expect. Quantum mechanics did not merely reveal strange particles or unusual experiments. It exposed a fracture between human intuition and the true structure of existence, a contradiction so deep that even the greatest scientific minds in history could not fully resolve it. Because somewhere beneath atoms, beneath space-time, beneath the visible architecture of the cosmos, the universe stops resembling solid reality and begins resembling possibility itself. Think about everything this implies. The particles forming your body were born inside ancient stars billions of years ago. Every atom in your brain emerged from cosmic processes unfolding long before Earth existed. You are part of the same universe now struggling to understand itself, a temporary arrangement of matter capable of asking impossible questions. And perhaps that is the strangest paradox of all. The observer and the observed may not be fully separate. For centuries, science treated humanity as external spectators, examining an objective universe from a distance. But quantum mechanics blurred that boundary. Observation became entangled with outcome. Measurement became part of reality itself. Not because human beings are magically controlling the cosmos, but because reality may be fundamentally relational at its deepest level. The universe may not consist of isolated objects sitting independently inside empty space. Instead, existence may emerge through interaction, probability, information, and connection, a cosmic process continuously unfolding. And if that idea feels unsettling, it should, because it means reality may be far stranger than human consciousness evolved to comprehend. Some physicists believe future discoveries will eventually restore order and reveal hidden mechanisms beneath quantum uncertainty. Others believe humanity has already uncovered the true nature of existence, and the universe is simply stranger than common sense allows. Right now, nobody knows which possibility is correct. That uncertainty remains one of the greatest unresolved tensions in all of science. And maybe that is where the true beauty of this story lives. Not in certainty, not in answers, but in the realization that humanity stands at the edge of an ocean of mystery far larger than itself. A species born on a small world beneath an ordinary sky somehow became capable of questioning the foundations of reality itself. Against impossible odds, consciousness emerged inside the cosmos and began staring back into the abyss of existence. And the abyss answered with paradox, particles that behave like probabilities, entanglement crossing impossible distances, measurements influencing outcomes, time behaving strangely, reality refusing to fully reveal itself. The universe is under no obligation to fit inside the limits of human intuition. And perhaps that is the lesson hidden inside quantum physics. Not that science failed, but that reality is deeper, stranger, and more astonishing than humanity ever imagined possible. Somewhere tonight, beyond the atmosphere of Earth, photons from distant galaxies continue traveling silently through cosmic darkness. Some began their journey before human civilization existed. Some were emitted before Earth itself formed. And now, after billions of years crossing the universe, a few of those particles may end their journey inside human eyes. The cosmos observing itself through conscious minds made of stardust. Perhaps that is what makes this contradiction so haunting. The greatest mystery in physics may not be hidden inside laboratories or equations. It may be hidden inside the fragile relationship between consciousness and reality itself. And if observing reality changes reality, what happens when the universe observes us back? Silence.